Good afternoon, everyone. Welcome to this webinar presentation. Let me present myself, Philip Ike, presenting to you from Australia, and Paul Bijou-Duval, who's back in the UK in a slightly more accommodating time zone. So the event schedule, we've got an introduction from me, technical sessions from Paul. We'll take a mid-term break for Q&A. Then we've got the second sessions and a panel session to close. Introduction-wise, so LUSAS version 22 went out in the last few weeks. The headline for this is Model Bigger and Faster. So we now have an open cascade front end. That's our geometry modeler. And that coupled with the 64-bit solver now gives you a continuous 64-bit experience right the way throughout the product. Not only can you model bigger, because obviously 64-bit allows you to address a larger memory space, but you'll notice speed ups throughout the software, and we're already getting extremely good feedback from our user base on it. The other side to this is that the new geometry modeler is a more modern modeler, and we're finding it far more stable. It's easier for us to develop into it. So I think it's good news all round. Also with LUSAS version 22, we continue our sustainability theme with the extension to the bill of quantities to include the carbon, the CO2 calculator. This not only offers you the ability to look at a single carbon option, but in a single model, you can look at different sustainability options, get an idea for the CO2 that's embedded in each, and use that to guide your design decisions. But today is about Grasshopper. We did a webinar back in March. That was on version 1. So version 1, our first release, had the basics of geometry, so mesh and the elements, beams, bars, plates, and shells, material sections, and loading. So and support conditions. So the basics really to create a simplistic model. We push that now further with the release in the last months of version 2, and then just very recently version 2.1. So version 2 features the customer and refer attributes. This allows, from Grasshopper, the addressing of any attribute inside the LUSAS interface. We will in time develop our own specific components which will connect with these, but the great advantage initially is that any user can connect with any attribute inside the software. And this is going to be a major topic for the presentations today. Also with version 2, we released the live update. So whilst you're running Grasshopper, you can hold LUSAS open and live push changes from the Grasshopper Rhino model straight into LUSAS. Version 2.1 sees us adding additional element types. I'd say the most important one of that is the plane strain element, and that's particularly useful for geotechnics where plane strain is much used. This also has an example today. Grasshopper is not the only plugin we have. We also have the Autodesk Revit plugin. We've had that for about 1.5 years now. It's good to see so many of our users downloading it. And similarly, we have the Tekla plugin. Both those are very similar in specification. And all of these plugins, we'll keep reiterating, they're free of charge. Initially, the Grasshopper one was chargeable. That's now free of charge, and it's the same now with Tekla and Robot. So for getting hold of the plugins, you need to go to the associated store. So for Rhino, that's Food for Rhino. If you just type in the search for LUSAS there, the plugin will come up and you can download it. You'll find worked examples on our website. So go to lusas.com to find those. And the examples that we do today, that Paul does today, will also end up back on lusas.com. Any assistance you need with the plugin, particularly the installation, please contact our best-in-class support assistants on support@lusas.com. So we're going to move now to session 1, and Paul, I'll hand over to you at this point. So 2 examples in this. We've got just a very simple geometry in the plate girder. focusing here on the custom and refer attributes. And then after that, we're going to move to the cable stay bridge. And one of the interesting parts to this is that it also features the push to Tackler as well as the push to LUSAS. So Paul, I'm just going to make you presenter now, and you should now have control.
Right, can you all see my screen? Phil, can you see my screen?
Yes, I can. Yeah, that's looking fine, Paul.
Okay. So just as an intro, as Phil said, you can download the plugin from foodforrhino.com. Just type LUSAS, you click here, and not only can you download the plugin, you also have access to the help manual and also to a series of scripts. So this is really the help manual. It covers the basics to get you started. And this is the web page that has for you about 10 or 12 scripts available for free. Just to give you ideas of what you can do with Grasshopper, there will be more and more scripts added to this web page. So now let's dive into Grasshopper, really, the core of this presentation. This is a very simple structure, and the point is not here to show you complex geometries, but rather the power of the custom attribute. So this is just a simple plate girder. It's straight, and the parameters are the span, the web depth, flange width, web thickness, and flange thickness. This is fairly simple here. You just define, the different lines and surfaces. All webs and flanges are modeled with the shell elements of surfaces. And as you know, as you download the plugin, you will have these components available for you. There's about 30 components. So you can define the main ones just as a very quick basic. You have the line member component to convert a Rhino or Grasshopper line to a LUSAS line. And same with surfaces. Okay, this is a B-rep, so you would attach a B-rep to this component and assign it to material, section, and mesh component. And when you're done, you have this LUSAS model component where you attach all your members, your analysis, if you have any defined and assignments that can be load assignment, boundary condition, and so on. That's the very basic. So here we have a simple plate girder. We have a material attribute, a section attribute, a geometric attribute for the web, and a mesh attribute, okay? And I can do the same for the flanges. Here I'm attaching this section attribute to the flanges, and I have also boundary conditions. So of course I know which points I need to assign these supports to, so I can just use this component here. On top of that, I've got a vertical load here on the top flange. And what you can see here, it's something that's new compared to the initial release of our plugin. We have this custom attribute component, which is available right here on the top right. This is the custom attribute. And here the define LPI and assign LPI. So LPI means this is really the LUSAS programmable interface. So it's like an API full LUSAS. And the real power is that any operation you do in LUSAS, almost any operation, is scriptable. So here, for example, what I wanted to do, I wanted to define not a linear elastic steel material, but instead I wanted to define a plastic material. So material that's got a yield strength, like a limit on the tension or compression I can get into my material. So I've added this piece of code here, which I've not written myself. I've just copied and pasted this code from LUSAS. So let me show you how it works. So I've got these two analyses, okay, here. And as I'm ready to push the model to LUSAS, I can just turn this Boolean toggle to true. And I'm going to here do this and create a new model. So now LUSAS is starting in the background. If you don't have an instance of LUSAS running, it will take a few seconds to open LUSAS and select the right license for you. But we also now cover live updates. So any change you make in the Grasshopper script will be conveyed automatically. If the Boolean toggle is set to true, will be conveyed immediately to LUSAS. If not, you can just leave the Boolean toggle as false. And when you're ready to push the model to LUSAS, you just set it back to true again, and it will be pushed. All the changes will be pushed to LUSAS. So here is the very simple model. Of course, you can see that the attributes were created correctly, including this steel plastic attribute. Okay, so I've got a 36 KSI limit here on the yield stress. And so how did I get the code? So for example, let me select, let me create a new material. For example, I'm going to call this steel plastic 2, and I'm going to click OK. And you see here in the LPI command output window, I've got these additional lines here. I've got set attribute, etc. So this really calls, this is the LPI code corresponding to the creation of this material attribute. So I can just copy these lines. Okay, so Control-C or right-click and copy, and go back to my script, and then just do here with a custom attribute. So double-click / to create a panels, which is just a text window, and paste. Okay, and this is really the same as what I had here. And I've got this additional line here because I just wanted to assign it to analysis 2. Okay, that's the only reason. It's not. This is really optional here. I didn't want to assign this plastic attribute to analysis 1, so I've added this piece of code here, which again is just the code I would get from LUSAS. And you can see that this custom attribute then feeds the custom attribute parameter here in the brep in the surface member component and also in the line member component. Okay, so it's a really nice way if you have an advanced material, because you see here we don't have so many components, we don't have hundreds of components. So if you want to define an elastic plastic material attribute, or maybe a concrete material that has creep and shrinkage, cracking, this is something you can get to in Grasshopper via the LPI. And that's really the power of LUSAS combined with Grasshopper. You can script anything. So I think everything's ready now to run the analysis. One thing I want to do here, because I've got 2 analysis and I've got a nonlinear material attribute, I need to add nonlinear control. So I'll do that manually, but I could also do that actually via the LPI. And I'm going to increase the load factor to 4 in order to see some non-linearity. Otherwise, everything stays elastic. So I'm going to change the load factor to 4, and I'm going to also add some type of geometric non-linearity. And I can just click run. This is a very simple model. Of course, nothing's curved. I don't have any initial imperfections. I could add these as a fraction of a buckling mode. But just for you to look at what of the output you can get in LUSAS, you can pretty quickly show the zones of plasticity, where the steel has yielded, and so on. So for example, here you have the nonlinear analysis. If I just go back here and show the, not the displacement, but rather the stresses, this is the pharmacy stress SE. I can see that, yeah, this is limited to 36 KSI, as I've specified. Also, if I want to look at really the points that have, the nodes that have yielded, I can just go to values and then select yield at the Gauss point. So I have shells here, I have thick shells, the Gauss points, and I can see that these integration points here on the top and also a little bit on the bottom have yielded. Okay, so this is just looking at some of the output you can get if you want to go into nonlinear buckling analysis in LUSAS. So that's it for this example. I'm going to go pretty quick because we don't have much time. So let me close this model and let me go now to something a little bit more advanced, not very much advanced, but just a little bit more. I'm going to show a very simplified, it's still simplified, of course, because this is just a demo, but I've got a simple cable stay bridge here. Yeah, this is pretty simple. Okay, so not meant to be realistic by any means. I've got these components in red because now my units are in meters, and the previous example was in inches. So I need to set it back to meters. Of course, I need to have some form of a unit consistency between Rhino and LUSAS. So you can see I have, this is really a 2D example, although the elements are set as 3D, but I'm restraining the torsion at the ends. So this is a 3D model of a cable stay bridge, and the parameters are as expected, just you know, the the span, the height of the pier, and the tower height, and the number of cables. Okay, so I can play with these parameters, of course. All these components are not LUSAS specific. They're just really Grasshopper native components to define the geometry. Okay, so I'm not going to spend too much time on these components. But here comes the LUSAS part. I've got, again, these line components to select the curves or the lines I've created in Grasshopper and attach to them a material, section, and mesh attribute. You will note that actually, let me flash the sections here by turning on the sections preview here. I've got this box section, but I'm actually implementing something more advanced. I told you about the custom attribute, so I'm using again here a custom attribute via the LPI. And the idea here is not to define just a hollow box section, but I want to define like a more advanced section with multiple cells. And so for this, I need a more advanced attribute. So again, I've done this in LUSAS once and just then copied and pasted the code corresponding to the creation of this attribute. Okay, so it's all parametric. You just do it once, copy and paste the code. You don't need to be an expert at VBS. This is by no means something we would expect from the users, but then you can really recreate any attribute, any utility. It's not only the attribute, it's the utility in LUSAS into Grasshopper. So then I've assigned this custom attribute to the deck, of course. Okay, this goes to the deck. So I've also defined my LUSAS attributes and assigned them to the towers and the piers, and I'm ready to push the model to LUSAS really. Let me set this to true. Yes, I'm going to create a new model here. Let me go to Grasshopper webinar for today. And this will take, again, maybe just a few seconds the first time you open a LUSAS model. It's even quicker if you have already a LUSAS open on your machine. This will create a LUSAS model. Something interesting that I want to show you is if I can push the same geometry to Tekla. So let's open Tekla now as the model is being created in LUSAS. Let's open Tekla. Let's open the model I had already been working on. So it's this one. Okay. And I'm going to actually delete the existing geometry that's going to appear on the screen to show you how it really works. So Tekla, of course, they've already developed their own Grasshopper plugin. So they have a family of components you can use in Grasshopper to push your scripts to Tekla. So yeah, I want to delete this because this is a saved model. So this would be easy, but let me minimize this. Let me minimize Tekla. Let me go back to Grasshopper and also minimize Rhino. And as you can see here, I've got these additional components. These are not LUSAS components. These are the Tekla components. So for Tekla, you would have this plugin with the Tekla plugins, okay, in Grasshopper. So very simple components. I am by no means, like literally by no means, a Tekla expert, but you can push your Grasshopper geometries, not only the geometries, but also the assignments, so the attributes to Tekla, okay? And very quickly, you get the 3D model in Tekla. Okay, this is a very basic model, of course. This is just a demo, but from here, you can of course go to drawings, create GA drawing. Let me check the scale. I want to check the scale. Yeah, I'm going to use 250 here. And then hit OK and open the drawing. So from the BIM model, of course, you can create any elevation sections, plan views, and so on. So the drawing is now being created, and you get the idea. This is a nice elevation. I don't have any labels on the different members. This is just a quick demo, but you've got the drawing. You can adjust the size, everything. You've got the title block here, but you get the idea. The general idea is we really have LUSAS, the FE engine, for a more holistic workflow where it's not only about the analysis, it's also about the design and documentation of your project. So let's now close Tekla. I don't need Tekla anymore. I can just go back to LUSAS. Let me maximize the Rhino form. I'm just used to having Rhino on the whole screen. Let me go back to LUSAS. Let me show you very quickly one of the things you can do in LUSAS. Let's turn off the loads. Let's run the model. I want to show you very quickly because this is something that's pretty useful in LUSAS. It's the linear tuning, the cable tuning facility. This will take just a couple of minutes, but it's really nice if you're working on this type of structures. So let me select the front view here. I don't need to look at the deformed mesh. I'm just going to select the cables here, select cables, and then I'm going to go to analysis, linear cable tuning analysis. I'm going to include all of these lines, and then the load case selected for the target would be LC1, which is the self-weight of the structure plus the additional dead load on the deck. And then for the targets, I'm going to select a few points. So for the points, I'm going to select as many points as lines to make the tuning analysis easier. So I've got about 44 points. And what I'm going to do on these points, I'm going to set a target of 0 vertical displacement. Okay, I can click OK, I can click OK again, and I can now run the analysis, the cable tuning analysis. One thing which is really nice with LUSAS for this type of problems, you can tune the cable force in each of these cables, which would be otherwise very tedious manually. You can tune these cable forces in order to achieve specific targets. It can be a displacement, it can be something else. It doesn't have to be a fixed target, but then you can calculate the forces in each of these cables to achieve, of course, a flat deck. So, of course, for cable stayed bridges, it would be for safety of the traffic and so on. You want a deck that's as flat as possible. That's something you could have actually for other types of structures, but it's important to be able to run some type of tuning analysis. So it will take another 10 seconds. This is a little bit slower now that I'm sharing my screen. So it's actually 2 or 3 times faster if I were not sharing my screen. But you get the idea. You can immediately calculate your optimal cable forces to achieve 0 displacement on the deck. So here it is. Okay, so this is Newton. So these are really, for example, 339 kilonewton. Okay, so I think Phil, that's about it. I'm running here. I'm being very quick because we have 2 or 3 more examples in this session, and this session is only 45 minutes long. So back to you, Phil, for now.
Okay, thanks, Paul. I'll just take. Can you make me presenter? Well, no, I can do it myself. Okay, no problem. Right, yeah, just a moment. Sorry. Okay, thanks for that. So we're going to move on to session number 2 now. So with the with what we've done in version 2, there's a few things we want to highlight to you as well. So we have the example. We've got a geotechnical example in this next session. So that's just a simple tunnel model using the plane strain capability. There's a interim example as well, but just one I've got on the screen here is the Helix Bridge. So you would have seen a photo of that earlier on in the presentation. That's an example of a much more complex geometry being run out of Grasshopper and Rhino and into LUSAS. So I think, Paul, just based on questions we have at the moment, because that was the other thing to do now, is just to take questions. I don't know. Do you want to take? See one on load factors there. I don't know if you want to answer that one, do you? Can you?
So
see
what's the question, Phil?
So it's can we assign load factors for different load cases in Grasshopper?
Yes, and you can also define any load combinations. I'm going to show this in example, not quite on the question of on the topic of load factors, but you can use the LPI not only to define more advanced attributes, but also to create more advanced analysis, to create branched analysis, and so on. I'm going to show this in the tunnel example.
Oh, okay, fine. All right. Well, look, let's move on with part 2 then, and we'll pick up other questions then at the end. So, Paul, I'll just hand presenter control back to you again.
Okay, so I hope you can all see my screen again. This is the Hello World equivalent in structural engineering of a very simple piece of code creating war and truss. But here, as you can see, I've got only LUSAS components here. How did I define the geometry then? I just use this Python component here. This Python component is available by default in Grasshopper. You just go to math and then click on the Python icon. You could do the same in Visual Basic, okay? Here I've created this parameter span, height, and number of panels. I can add additional parameters if I want to. And you can create any code. You can write any sort of code in the Python to create your geometry. That's in case you want to create something where you really have full control over the code, and maybe you don't like the way Grasshopper works with all the wires going everywhere if they're not if they're not organized well, if not some of them are hidden and so on. So you can easily get a very messy platform on Grasshopper, a very messy script in case you don't pay attention. Usually you should not, okay? But you can also create your geometry parametrically in Python directly within Grasshopper. So here I am really writing a function. And for these simple geometries, actually, you can even use the power of AI and just ask ChatGPT to create you something. That's totally fine for the first start, of course. You would not trust that later on. But for a very first start, just, understand the logic, that's totally fine. So here I'm really writing a function, and the result of this function are these lines. And then based on these lines, I can, again, reuse my LUSAS components, all of these components to attach to these lines, material, geometric mesh attributes, and so on. Okay, so it's another way of defining structures parametrically. We of course have the possibility to script anything in VBS or in Python in LUSAS since version 21, but you can also use Python directly in Grasshopper. That gives you the ability to visualize your structure before it is being pushed to LUSAS. So let me click true again. So I'm going to now go to, oh, it's not this one, desktop, Grasshopper webinar in June. Today, I'm going to create a new model. I can also open a new model. Okay, you don't have to create a new model all the time. Something I want to show you here too is the live updates, because we've mentioned that. It was not covered in the first release of our plugin, but it is very, very useful. You don't have to close and reopen LUSAS again anytime you make a change to your script, which was annoying, of course, because you want to be able to immediately visualize the changes of your model. So this is the very simple Warren truss. I'm not going to run the analysis because it is really extremely simple, but let me minimize this form here, and let me change a few parameters in the Grasshopper script. Let me close this. Okay, maybe I want to, and this is set to true. Okay, so maybe I want to do, I want to increase the span. So maybe I want to do, I don't know, 55. Okay, you see this window. It is updating the model in LUSAS. Okay, so now it is longer. Maybe I want to do 12 panels instead of 8, and so on. So this is also now being updated in LUSAS. Okay, so you can see the live updates between LUSAS and Grasshopper. That's it for this, again, simple example. Here, the idea was to show you the power of Python directly within Grasshopper. Let me close this model. Let me close this script. And let me show you something now, a little bit, just a little bit more advanced. It's a soil structure interaction model, tunnel stability in 2D, so using plane strain elements. Here you can see my parameters are just the width, the depth of the tunnel, the diameter of the tunnel, and another geometric parameter for the depth, I believe. I'm just modeling half of the structures of the structure, so I'm applying lateral boundary conditions here to make sure I have a symmetric response. I don't need to model the full surface, but as you can see, the tunnel is here. Just these basic components to define the geometry. And then I have the custom attribute component to create this mole Coulomb attribute for the soil. Okay. I also have another attribute. You can actually use just a single custom attribute component to create two attributes. Here I'm using the displacement reset attribute. That's something you often do in soil problems. And I'm attaching these to the surfaces that are modeling the soil. Okay. Something else that I have, you can see I have these additional yellow boxes. These are just pieces of code, pieces of LPI commands that I've copied from LUSAS to define my nonlinear controls, and also to create the branched phi-C analysis. So phi-C analysis is a type of analysis where you study the stability of your soil. And I have this phi-C attribute, and I'm also assigning this phi-C attribute to a specific load case, which is why I have this additional piece of code. Of course, again, I haven't written any of these lines one by one. This would be absolutely crazy. I'm just copying them from LUSAS the first time, and then it stays in the code. I've also got an additional custom attributes to define and assign a phase load. Okay, you can't see any phase load here, so I need a custom attribute. And now that I'm ready to push this to LUSAS, I can just double click here and set it to true. I'm going to do this. And it will create the model. This will take a little bit more time now, because every time I have an append, so an append is a piece of code that I add to the end of the script. And in this case, I'm creating the phi-C analysis. I'm creating this branched analysis. It is remeshing the model. I could be smart and lock the mesh. Unfortunately, I'm not smart enough yet. But so for next time, I'll do it. But otherwise, you have LUSAS remeasure your structure each time, which is fine. In this case, this will just take another 20 seconds. Let me maximize also the window when I can. And so here, as you can see here in Grasshopper, this is a 2D in-plane analysis. This was not available in our initial release. Okay, so now you've got access to all the 2D plane strain, plane stress elements, 2D analysis, 2D attributes, really. So you can, if you're a geotech engineer, that can be of use for you. Okay, now, it is remeshing it again. I think it is about to be done. It is done. And as you can see, I've got my advanced attribute here that I was able to create using the custom attribute. It's a mole Coulomb, okay? It's a modified mole Coulomb material attribute. This is actually one of the benchmark examples from the Plaxis website. We've benchmarked our geotechnical capabilities against Plaxis using about 30 to 40 problems, and we've got now a pretty powerful geotech module. You can see here as well the phi-C reduction attribute and the displacement reset attribute that I had defined parametrically in Grasshopper. You can also see here the branched analysis at the end of the main analysis. A1 is the main analysis with load case 1, and at the end of load case 1, I just want to look at the stability of this structure. So I can just click run and look at the stability of this. Another thing I want to show you, because I haven't covered that yet, is the refer attribute component. I've talked a lot about the custom attribute component. We've also got access to the refer attribute component. What it does, it will look for all the existing attributes in your model. If you just double click on show LUSAS attributes, and it will find the available components. Okay, so if you want to create, say, another more Coulomb attribute, you would just go to isotropic material, copy name, okay, and then double click, double slash to create a panel, and then enter. That would be for the name, and for the type, that would be copy type, okay, double click, slash slash, control V, and that would be the type of this attribute. And I could again then attach this to my line or to my surface. In this case, it would be a surface because the soil is represented with the surface. So that's another way of defining any advanced attributes in LUSAS. I usually prefer the custom attribute slightly because you don't need to have any existing attribute in LUSAS. You just look at the LPI code corresponding to this attribute, but that's another smart way. The refer attribute is another smart way of creating advanced attributes. Okay. So let me close this and let me go back to LUSAS. I'm going to run this in the background. It's going to take a few minutes just because I'm sharing my screen and it's eating up a bit of memory. I don't have the most powerful laptop, although it is very, very much fine for this. Instead, let me go back to Grasshopper, close the existing script that I have open here because I don't need it anymore because now the analysis is running in LUSAS directly. I can close this. And I can open the final example. We have only 6 minutes available, so let me open this very quickly. I'm going to open the Helix bridge, the Helix footbridge in Singapore. I have not worked personally on this bridge, and by the way, I have not stolen any kind of classified information to create this script. I'm just using publicly available information, available data on this bridge regarding the the diameter of the helices and so on. There is a really smart individual on YouTube. He has shared a series of videos where he goes over the creation of a Grasshopper script, but he's an architect, he's not an engineer. So at the end, what he wanted to do really was to produce some nice renders. In my case, although I really like architecture and nice renders, I was more interested in creating a structural model. So I had to adjust the script to produce these structural components, lines and surfaces, and so on. And I think I'm just going to close this because otherwise it's eating too much memory on my computer, and the more complex script on Grasshopper can't even open. Let's see how far it went in LUSAS. Yeah, I already got to 1.1 as a stability factor. Yeah, I've got this error message, of course, because I've manually told LUSAS to stop, okay? But the final safety factor would be 1.215, okay? But you get already the idea of this instability in just above the tunnel, okay? Let me close LUSAS because I really want to hear your questions. This is the script. It's a more complex script, of course. What do you expect? You've got something for the cross beams, and of course for the main helices, the minor helices, and all the viewing pods, and so forth and so on. Okay. Again, I have used like an existing series of existing videos, but then I've changed a lot of that to create this structural model using this LUSAS components, okay, for the surfaces. And let me show here the full names of the components. Draw full names of, yeah, so the major helices, minor helices, edge beams, columns, etc. Let's have a look here at the model. I want to select a perspective view, and here, yeah, there is the structure. I'm not sure about the radius of curvature. I don't have access to the bridge drawings, but I made my best guess using Google Maps. And you have everything from the major helix to the minor helix, the viewing pods, the deck, the cross beams, and so forth and so on. I'm just going to open here the LUSAS model equivalent to corresponding to the script, really. I could push this to LUSAS, of course, but this would take a few minutes, and we don't really have the time here. It's a much more complex script, of course, and I have no idea how you would create this geometry in LUSAS directly. We do have a geometry engine, a 64-bit geometry engine, but you may have the best geometry engine. It's very hard not to create this in a parametric fashion, of course. So yeah, my license will expire, but that should be fine. I'm going to open the footbridge model. It is right here. So LUSAS, it's not only LUSAS and Grasshopper. This is not only to create complex geometries. I have this fancy model at the end, but you can create also pretty simple geometries or models. But if there is anything repetitive in design, things change all the time. So you don't want to recreate your model from scratch. So it's very nice to be able to parameterize things in Grasshopper and then be able to push your geometry not only to LUSAS for the FEA, but also to Revit or Tekla for documentation. That's a very powerful workflow. Okay, that's the whole idea. The idea is just LUSAS is part of a bigger ecosystem, a bigger workflow, and we want to make this workflow as seamless as possible for designers. Yeah, so here is the final geometry. I've just pushed the script. Yeah, here it's a really nice model. The mesh is fully connected. I can look at a more close-up view here, and yeah, I think it is a pretty nice model. So with this, back to you, Phil. I'm done with the few scripts I had to show for today.
Okay, thank you, Paul. And that brings us to the end of the technical side of the presentation. So just to pick up on something that Paul was also showing there was obviously the Python side of things. So Python as capability in LUSAS, that was part of version 20, I believe, or 21. Anyway, it's been in the software for a year or two. So Paul's demonstrated that there inside Grasshopper. What you can see on the screen here is how now in the command window you can just separate out the LUSAS programmable interface commands. You can see those either in Python or Visual Basic. Copy and paste those around. So that's very nice to work with. So, sorry, I've just got problems with my screen here. So yes, with anything that you see in that echo window, you can copy it out to other programs like Paul did there, copying it back into Grasshopper, save it away, edit it, turn it into a parametric, and reuse it. So Python coding definitely is a way forward. We're also at the moment working on a repository, an online repository through GitHub, where we will host a lot of the codes that we do for Grasshopper, Python, Visual Basic, C#, and other languages. So the idea behind this is that it's example code for you as users. We'd also like to see some sharing and some collaboration going on there. We appreciate for many clients, they maybe prefer not to share their code, as they might see it as some competitive advantage to their own firms. But we're interested really to see how this goes, and it should help everybody that's interested in coding greatly. So just to summarize then, we've been talking about predominantly version 2 of Grasshopper, version 22 of LUSAS, and version 2.1. So Paul spent quite a lot of time there on the custom and the refer attributes. So you can see the refer attribute component on the screen there. And again, this will give you access to everything that we haven't currently programmed a direct link in for right now. We will get around to these things in time, of course, but in the meantime, it gives every user the chance to reach every attribute inside LUSAS. We also Paul talked about the live update, so controlling LUSAS live from Grasshopper, and every time you make a change, pushing that through, if you want to, through to LUSAS. And we had a example there in that last session, obviously, of the plane strain capability now. So that's version 2.1 of the Grasshopper plugin. There are other element types in there as well, including grillage and some others that I don't remember immediately. So anyway, that is the presentation for today. We've got, Paul, if your mic is still live, we've got a few questions on the panel here. I don't know if you want to take some of those.
Yeah, can we script the VLO and so that's one of the things that's not currently scriptable in LUSAS. You can define your influences. Influences are just attributes, so you can use the LPI to create custom attributes in Grasshopper to create the influences, but the VLO itself is not scriptable at the moment. So yeah, probably in maybe not the immediately next release of the plugin, but maybe the one after that, or the one slight maybe after that, but not too far away. I mean, we will have that also covered in Grasshopper, so that you can not only create your model, but also set up all the analysis, including the live load analysis, so the VLO, the vehicle load optimization in LUSAS.
A question has just appeared whilst you're talking there, Paul, on shell modeling and connectivity.
On the shell modeling and connectivity, so I guess the question refers maybe to merging of the shell. So in Grasshopper, what will be done at the end is merging of surfaces at common lines and so forth. So maybe you have a block of code in Grasshopper that deals with, say, the walls of your structure, and another part with the slabs, you know, of your structure. Then the script, I mean, the plugin will merge the edges. Okay, so that's a nice feature. By default, common features will be merged.
Okay, I'll take a question here. It's just come in. I forgot to mention it earlier, actually, which is every time we do a webinar, we also record it. Then some days after the presentation is done, everybody that's signed up will get a link so they can go and watch the recording. We also put the recording up on our website just for general consumption. I think it certainly goes to YouTube, possibly some other platforms as well. So yes, once we've done this live session today, you'll get that coming through to you by email. And then as this user is asking here, yes, of course, you can then share that around your teams and share it with others that couldn't make it today.
Yeah, I'd really like to emphasize that once we release this GitHub platform, I'd really encourage everyone to upload a piece of script, a piece of code they've created themselves. This is to build a sense of community among LUSAS users, not only for us to showcase our scripts, because we know we've got some very smart users all over the world, and they don't have to share the whole script, the whole thing, the whole project, but if they can share some of it to give ideas, that would be great.
Yeah, I think that's a good point, Paul. We've just had another one coming in here about grillages. I can't see the whole question.
So yeah, we'll have a more comprehensive grillage wizard in LUSAS in version 23. Grillages, of course, they're not the most refined methods to analyze the structure, especially if it's curved, but if it's mildly curved or straight, that's totally fine. Yeah, wizards, of course, are another way to define things parametrically. We also have an FCM wizard, so that's for balanced cantilever bridges. We have a wizard for curved steel concrete composite bridges. That's also a wizard. Remember, though, that a wizard has limitations built in. That's inevitable, unfortunately. So if the wizard can cover what you want to do, that's great. But if not, you might have to go back to Grasshopper, Python to define what you want to define, okay? Especially if it's a very complex, say, a bridge alignment or something like this, maybe an S-shaped curve or something like this.
Okay. I think at that point we might be done for now. So we're going to leave this session open anyway. Obviously, anybody can contact us directly by email after the event if other queries come to mind. We'll answer those as they come in. But otherwise, I think, Paul, it's probably good for us to just thank everybody for attending, and we'll see you at the next event. There will be a version 3 upcoming. I didn't have a slide on that here, but one of the things that we have coming up next is volumetrics. So Paul obviously showed an example of a plane strain model there for geotech. Geotechnics as well is quite reliant on volumetrics for modeling the soil continuum, so that'll be a next development. Paul, you're obviously closer to the development of the plugin than I am. Is there anything else you'd like to say about what's coming up next?
What's coming up is really the volume attribute, the ability to define really solid models, but also the point component. You saw we have the line member attribute, the line member component, the surface member component. So we'll have the volume as well. But to really close the circle here, we'll also have the point component in case you want to have point joints, point masses. Maybe you have a tuned mass damper somewhere on your bridge. You want to do that with point masses. You can also parameterize that in Grasshopper with the point component. We'll also have the activation and deactivation attribute, and we'll keep adding components, the influences, and so forth and so on. Of course, we're also working on the path utility to be able to define tendons parametrically and be able to then adjust the position of the tendons if your bridge alignment changes. That's something that's coming out very soon. So stay tuned, and feel free to download the plugin. It's free anyways. You can download the scripts. You can use your own scripts. You can use your Grasshopper scripts and add some LUSAS attributes to it, and then push that to LUSAS, see how it works, how it compares with maybe the other structural software that you're using at your firm. It will keep evolving very fast. We're moving very fast on this because you've got very good feedback.
Yeah, and that feedback is extremely important. So we appreciate those users who have been so open with us about what they want next. That really helps guide us in the development. And I think as we've proved so far, the release cycle on this is a tight release cycle. So we've so far released every 3 months or so, or even maybe more quickly than that. So as Paul says, stay tuned. There'll be more updates presently. But otherwise, thank you again for attending, and we'll see you all again in the future. Thanks, and
thank you.
Bye from me.
Bye-bye.